All right, this is Mr. Jern, and I have here a position versus time graph, sometimes called a distance versus time graph, basically the same thing. I've got 4 questions here. We had to calculate position, velocity, and distance traveled along with displacement. And so to do that, there's a couple things to remember. First of all, this applies to position or distance versus time graphs, not any other kind of graph because of the relationship between the 2 variables. So to get position on a position time graph, you simply read the graph. So we need to find the object's position at 3 seconds, 4, 7, 9, and 12 seconds. So I notice that position is on the y-axis and time is on the x-axis. So if I want to know the position at a certain time, like for example 3 seconds, I go over to 3 seconds and I see that the position of the object is at 1 meter. At 4 seconds, looks like the position is still 1 meter. At 7 seconds, I go over to 7, I go up, and it looks like the object is at 4 meters. At 9 seconds, I go over and don't have to go up, it's at 0 meters. For 12 seconds, looks like the object has moved back to -2 meters. So that's basically it for position. You read the graph, nice and simple. For velocity at those letters, velocity on a position time graph is you find slope. And to find slope, we're going to have to use the slope equation in a moment, but I'll show you that. But when it's talking about A, B, C, D, E, it doesn't specify exactly where on the line segment we're talking about, but that's okay because when you're talking about a line segment, we're going to assume that the entire line segment is continuous and straight, and it looks like it's representing what it is representing. So we start at 4 meters and it goes down to 1 meter, and it takes 3 seconds to do that. So we're not going to make any assumptions when we have a graph like this unless it says otherwise. We're going to assume that what we're seeing is what it's representing. So to find the velocity, we have to find the slope. And because of what I just said, the entire line, if we find the slope of this line segment, that's the velocity for the entire line segment, because in a position time graph or distance time graph, slope is speed, velocity, and velocity is slope. You could just switch the words and you're good. So to start with, I'm going to remind myself and write down the equation for slope. All right. This is something that, well, you probably have used many times now. It's change in y over change in x. You're going to find the change in something. We don't do that. Let's try that again. It's the change in y2 minus y1 over x2 minus x1. And that's how we're going to approach all of these. So when you're finding slope of a line segment that's pre-drawn like this, I just suggest using the endpoints because the endpoints, like I said, are where they seem to be. So for segment A, it looks like our endpoint is at right here. And so at 0, 4. And the other endpoint is going to be right here at, was at 3. In fact, let's write out the coordinates here. So this is 0, 4, just to be sure. And this one will be 3, 1. Okay. And we might as well just go ahead and we know, come on, we know we're going to have to, this is not behaving itself. We know we're going to have to do all these later. So this is what, 4, 1. So we might as well just prepare ahead of time. And this is, what is that, 7, 4. And, you just, PowerPoint, trying to do something here. So this is what, 10, -2. And this one, I don't think we're going to need that one, but I'm still going to write it out anyway, just because I'm on a roll here. Okay. So for my first one, what I'm going to do is I'm going to call this one x1 and this one y1. I'll call this one x2 and y2. Okay, and things may change depending on the situation you're in. So for the slope of A, I will take y2, and I've already got them. So like I said in class, I pre-label them so that I don't have to think about it right now. I've already thought it through. I already know that y2 is going to be 1, and it is a, that would be what, 1 meter. It does have units and meaning in real world. Y2, oh, hey, I look ahead of myself. See, this is why I do this. When you draw and plan out everything, you will catch yourself making mistakes. So y1 is 4 meters. I was right. Not to be confusing or anything. y2, oh, I see what happened. This 1 looks like a 2, or 2 looks like a 1. Let's rewrite that. Clarity is going to be very important here. Hey, come on, really? So 2 minus y1. So y2, as I have it labeled and it was correct before, is 1 meter. Why is this not liking me right now? 1 meter minus 4 meters is going to give me, divided by x2, which is 3 seconds, minus 0 seconds. And again, I've got them pre-labeled, which I was second guessing myself a minute ago, but then I just went back to what I've already thought about and wrote down, and it made a lot more sense. So 1 minus 4, I'm going to actually write this down, is going to be negative 3 divided by, that's meters, divided by 3 seconds. And so for letter A, my slope is going to be a negative 1 meter per second. And as I said before, put a box around that, and that is your that indicates that is your final answer. So that's it. It's a negative slope. It means it's going, I guess we'd call it backwards or in the negative direction, and that goes along with the fact that it is a negative slope on the graph. For line B, well, you can do the math, but it's a horizontal line, so we're not going to have to, I mean, there's no reason to waste our time calculating the slope of a horizontal line. It's always going to be 0. Letter C, this will probably be the last one I do. Well, maybe we'll see. Letter C. Okay, so for letter C, this is going to be my x1, y1 for letter C, and this will be my x2, y2 for letter C. Just going left to right. So looking at my equation, y2 is 4 meters, and I know it's meters because it's on the y-axis, and the unit is meters, minus y1, which is 1 meter. Okay, see, I'm going kind of fast because I've already written it down. I don't have to think about it. Well, where's y1? Where's y2? Is that a y or is that an x? My thought process was focused on identifying x1 and y1 and then x2 and y2. And so I was able to 100% commit to that. And now I'm 100% committed to putting those into the equation in the correct spot. So I don't have to think about 2 or 3 things at a time, although I am trying to talk while I do this, which is distracting. And so you should try to avoid distractions when you're doing this. Doesn't matter if it's the first time or the 1,000,000th time. I've been doing this a while, and as you can see, I get easily distracted and make mistakes as well. So x2, looking at my equation, is 7 seconds. I second guessed myself and I double checked, and past me was correct. And y1, see, x1 is 4 seconds. Write things down. So when you second guess yourself, well, you have something to go on. All right, so 4 minus 1 is 3 meters. 7 minus 4 seconds is 3 seconds. So now we're going to get a positive 1 meter per second. Now, do you need to put the positive there? No, it's always implied, but I did it just because I wanted to make sure we understood it was positive, which makes sense because once again, the slope is going upward. Letter D. Okay, I'll do one more. Well, actually, I might as well do them all because then letter E is going to be easy as well. All right, letter D, let's see. I've got x2 and y2. I'm going to just kind of put a line through that because I'm done with that. This will be my x1 and y1 for letter D. And then down here, this will be my x2 and y2 for letter D. Okay, so y2 is -2. We can deal with negatives, meters, minus y1, which is 4 meters, divided by x2 is 10 seconds, minus x1, 7 seconds. -2 minus 4 is -6 meters. 10 minus 7 is 3 seconds. And so I get a slope of -2 meters per second. Nice, I didn't have to pick up a calculator for this one. But I would suggest just double checking. Well, 6 divided by 3. I guess we could do that without the calculator. And then I'll just do letter E because it's a horizontal line, and we all know horizontal lines are 0 meters per second. Now I put that slash there because through the 0 so that we don't confuse it with an O. All right, so that is how we do velocity. Oh, there's distance already there for us. So that's how you do velocity. That's how you calculate velocity on a graph like this, position versus time. So now question 3 asks us for the distance traveled during these time periods. For distance, it's a little trickier. You had to sum all the changes in position ignoring direction. So it doesn't matter if it's positive or negative, you still have to move that distance. As I mentioned in class, think about running back and forth. It's not like you gain back all the energy you lost when you run backward or to where you started from, because you're not really running backwards usually. If you run in a circle, the direction changes, but you still run the distance. So it's the amount of ground covered. All right, it's the amount of ground covered. It's exactly what you think of it in distance. So how do you do this in a graph? So it says sum all the changes in position ignoring direction. So what I'm going to do is go through each line segment and figure out how much distance changed. So from 4 meters down, from between A and B, basically for part A, it goes from 4 meters down to 1 meter. So the change here was 3 meters. So I'm trying to find distance. I'm going to put a little asterisk here so we know red is the distance. Letter B here, nothing's changed. That's going to be 0 meters. Letter C, it goes from 1, okay, all the way up to, so it goes from 1, this first part here, and it goes up to 4 right here. So the change once again is 3 meters. Now, yeah, it's the same as the other one, the first one, in the opposite direction though. Okay, that doesn't matter though, because this object went backwards 3 meters, stayed there for a second, and then went forward for 3 meters, or in the positive direction for 3 meters. I mean, yeah, it ended up right where it started from, but it still traveled the total of that I mentioned. So now this next one goes from 4 meters in the positive to -1 meter, or I'm sorry, -2 meters in the negative. So the total change here is 6 meters. Okay, so now we're getting at, oh, what happened? So for all of these, I've been doing it in my head, and probably you have too, maybe up to a certain point. And maybe that was throwing you off. So how am I figuring all this out? Well, change in anything. So I'm figuring out the change in position or in distance. So I'm going to use the distance, I guess. I guess I could use a P for that. Let me just erase that. So I'm going to find the change in position. Now there is a symbol we could use in physics for position, that's X. But in fact, I'm going to do that right now just to be consistent with, I don't want to shortchange here your education. So to find the change in X, to find the change in anything, you basically take where you are minus where you were. Okay, in other words, where you are is the X, where you were, this little 0 here means that's where you started from. Hey, that's where you started from. I thought we were past this PowerPoint. So that's what that little 0 means. Oh, I know why I hit the keyboard. So more practically speaking, let's take a look at this line segment D. It ends at -2. So I'm going to stop at -2 meters, and it started at 4 meters. Okay. Really though? Oh, I'm going to regret writing that. It ends at 4 meters. So it started here. Holy cow. PowerPoint just doesn't like me right now. It's probably mad I don't spend any more time with it now that we're not remote. So it started at -2 and it ended, or it started at 4 and it ended at -2. So you take where you are minus where you were, and that's where I got the, well, it's a -6, but the total distance traveled is 6 meters. Doesn't really matter. We're not concerned with direction when it comes to distance. So knowing I'm going to have issues with that, I'm going to rewrite that equation over here. How do you find the change in anything, specifically position? Well, x minus x, it's called x naught, or it's basically where you are minus where you were. All right, that's what it's basically, not even basically, that's what it's saying here. Where you ended up minus where you started from. Okay, and this last one, once again, is going to be 0 meters. It didn't change at all. So to answer the question, from 0 to 4 seconds, it looks like the distance traveled between 0 seconds and 4 seconds is, oh, what, 3 plus 0, so 3 meters. All right, from 0 to 7 seconds, from here to, let's go to 7, is right about here. Looks like the change is 3 plus 0 plus 3 going back. Direction doesn't matter because you still have to travel that. So the total is 6 meters. Okay. And the last one, going from 0 to 12 seconds. Well, let's do this down here, I suppose. 0 to 12 seconds. How much is that going to be? Well, it's 3 plus 0 plus 3 plus 6. So it ends up being 12 plus 0, I guess. 12 meters. 12 meters to go from beginning to end. Back and forth a little bit at the beginning, and then it's like it had to check. It's like, where should I go? Oh, and then it went back to like check its directions. And then it decided where it needs to go, and it ended up going there. So that's distance. Sum all the changes in position. Finally, what is displacement? Displacement, the overall change from initial to from final to initial position. Okay, kind of similar to this little equation, what was going on here, except actually not even kind of similar. It's basically using that equation, except we actually do pay attention to the direction. Okay, so from 0 to 4 seconds, the displacement. Well, where was it at 0? It was at, well, let's see where it ended. How about, let's start with there. So it ends at 4, it's 4 seconds, and at that point it is at 1 meter. So for 0 to 4 seconds, it ends at, I wrote the 4 again. It ends at 1 meter. It started at 4 meters. And so the overall displacement is -3 meters. Okay, which makes sense because if you think about another way, it started right here at 4. Started right here at 4, and it moved down to, it moved down to 1, and going from 4 to 1, well, you move -3. So that's simply how you do it. So from 0 to 4, that's how you do it. From 0 to 7 seconds, well, once again, at 7 seconds, where was it? It ended up at 4. At 0 seconds, where it started from, it was at 4 meters. And so the total displacement is 0 meters, which again makes sense, because if you look at the graph, we started out here at 0, we ended up right here at 4, we ended up here at 4, 7 seconds later, and we ended up right where we started from. So your overall displacement, your overall change from final to initial position has been 0. Finally, 0 to 12, 0 to 12 seconds. Well, at 12 seconds, we're at -2. So right here, it's at -2 meters. We started out at 4 meters. And let's just do this. And I'm just going to cross that out because ignore that question. So I should have done this correctly. Erase. Okay. So -2 minus -4 gives me a -6 meters. So the thing on the right in the purple is a mathematical representation of what you can visualize perhaps from the graph itself. So once again, we start over here at 4 meters and we ended at 2 meters right here, -2 meters. And so in that 12 seconds, we went from 4 all the way down to -2. And so to do that, you had to travel backwards 6 meters. All right. So technical gaffes aside, I hope that was helpful to you. Like usual, please let me know if you've got any questions. Essentially, this is a summary of almost everything you can do with a position time graph. All right. So practice that up. Let me know if I could do anything for you. And good luck. Take care.